Let's start with a simple idea. Imagine a processor that completes one instruction every clock cycle. One instruction enters, one instruction finishes. Clean, predictable, efficient. But then someone asked a dangerous question. What if the processor could complete more than one instruction per cycle? Not by increasing clock speed, not by adding more cores, but by doing multiple instructions at the same time inside a single core. That question gave birth to superscalar architecture, and superscalar design is one of the biggest reasons modern CPUs feel fast. Not just fast in marketing terms, fast in actual instruction throughput. Today we're going deep into how this works. We'll cover what superscalar really means, how the hardware makes it possible, what limits it, why instruction-level parallelism matters, how compilers influence performance, and why memory can silently destroy everything. This is one of the core pillars of software execution, so let's begin properly. First, we need to understand the limitation superscalar was designed to solve. In a basic scalar processor, only one instruction is issued per clock cycle. Even if the pipeline has multiple stages, the front end only feeds one instruction at a time. Fetch one, decode one, execute one. If the pipeline is 5 stages long, you may have 5 instructions in flight, but still, only one new instruction enters per cycle. That means your theoretical maximum IPC, instructions per cycle, is 1. Now think about real software. Programs don't consist of one instruction, they consist of millions, and very often, multiple instructions are completely independent of one another. If you calculate A plus B, and then separately calculate C plus D, there's no reason those two additions must wait for each other. The only reason they execute sequentially in a scalar CPU is because the hardware only allows one instruction per cycle. That is the bottleneck. Superscalar architecture removes that bottleneck. The word superscalar simply means that the processor can issue multiple instructions per clock cycle. 2 wide means 2 instructions per cycle. 4 wide means 4 instructions per cycle. 6 wide means 6 instructions per cycle. Not multiple cores. Not multi-threading. Multiple instructions inside a single core in the same cycle. If everything aligns perfectly, a 4-wide processor could complete 4 instructions every cycle. That means IPC equals 4, at least in theory. But here's the key. Superscalar does not guarantee multiple instructions per cycle. It only makes it possible. Whether it actually happens depends entirely on the software and the microarchitecture. To execute multiple instructions in the same cycle, the CPU needs multiple functional units. You can't execute 2 additions simultaneously if you only have one arithmetic logic unit. So superscalar processors include multiple integer ALUs, multiple floating point units, multiple load and store units, sometimes multiple branch units, and vector execution units. Each instruction is dispatched to an appropriate unit. If 2 instructions both need an integer, ALU, and you only have one free, one instruction waits. That's called a structural hazard. So superscalar throughput depends on available hardware resources. Now let's talk about instruction-level parallelism. Superscalar architecture only works if the program contains independent instructions. If you write a sequence where each instruction depends on the result of the previous one, the CPU has no choice but to wait. Consider a chain of calculations where each result feeds into the next. That creates a true dependency. The second instruction cannot execute until the first one finishes. In that situation, even a 6-wide processor behaves like a scalar processor. On the other hand, if multiple instructions operate on unrelated data, the CPU can execute them in parallel. This property, how many independent instructions exist at a given moment, is called instruction-level parallelism, or ILP. Superscalar hardware is designed to exploit ILP, but it cannot create ILP out of nothing. It can only discover and schedule what already exists in the instruction stream. And here's something important. Most real-world software does not have unlimited instruction-level parallelism. Studies show that general-purpose code often exposes between 2 and 4 useful instructions per cycle on average. That's one of the reasons CPUs rarely go extremely wide. Now let's move to the front end of the processor. If you want to issue 4 instructions per cycle, you must fetch 4 instructions per cycle. That means your instruction cache must supply enough bandwidth. Your fetch logic must handle wide access, and your branch predictor must be extremely accurate. Because every time you mispredict a branch, you flush not one instruction, you flush multiple instructions that were speculatively fetched and decoded. The wider the machine, the more painful branch mispredictions become. Superscalar width amplifies the importance of branch prediction. Now consider decode. On architectures like x86, instructions are variable length. That means the decoder must find instruction boundaries and translate them into micro-operations. Doing this multiple times per cycle is complex and power-hungry. Modern CPUs solve this with micro-op caches. Once instructions are decoded once, their micro-ops are stored in a special cache. The processor can then skip the expensive decode step on subsequent executions. On RISC architectures with fixed-length instructions, multi-instruction decode is simpler. This is one reason RISC designs scale more cleanly to wider issue widths. Now we need to discuss dependencies more carefully. There are 3 major types of instruction dependencies. The first is a true dependency, also called read after write. That's when one instruction needs the result of a previous instruction. These cannot be eliminated. The second is write after read, called an anti-dependency. The third is write after write, called an output dependency. These last 2 are artificial. They exist because instructions reuse architectural registers. Superscalar processors eliminate false dependencies using register renaming. The processor maintains a larger pool of physical registers than the architectural registers visible to software. When instructions are decoded, architectural registers are mapped to new physical registers. This removes false dependencies and allows independent instructions to execute in parallel. Register renaming is absolutely critical for wide superscalar execution. Now let's differentiate between in-order and out-of-order superscalar designs. An in-order superscalar CPU can fetch and decode multiple instructions per cycle, but it must execute them in program order. If the first instruction stalls, everything behind it stalls. This limits performance. Out-of-order execution changes the game. Instructions are still fetched in order, but once decoded and renamed, they enter a scheduling window. The processor looks for instructions whose operands are ready and whose required functional units are available. Those instructions can execute immediately, even if earlier instructions are waiting on memory. This keeps the execution units busy. Results are temporarily stored. Eventually, they commit in program order using a structure called the reorder buffer. This ensures architectural correctness while allowing dynamic reordering internally. Out-of-order execution is what unlocks the real potential of superscalar architecture. Without it, width is heavily constrained by stalls. Now let's talk about the issue queue. After decode and register renaming, instructions enter an issue queue. Each cycle, the processor checks which instructions are ready. Ready means their input operands are available and a functional unit is free. The scheduler selects up to n instructions, where n equals the issue width, and dispatches them to execution units. As width increases, scheduling logic becomes more complex. The processor must track dependencies among many instructions in flight. This complexity grows rapidly. The hardware cost of supporting very wide issue grows faster than linearly. It affects power, latency, and silicon area. That's why you don't see 16-wide general-purpose CPUs. Now we need to address the elephant in the room. Memory. Memory latency is the single biggest enemy of superscalar efficiency. If a load instruction misses the L1 cache, it may take hundreds of cycles to fetch data from main memory. Out-of-order execution can hide some of that latency by executing other independent instructions. But if too many loads miss, the reorder buffer fills. The issue queue fills. Eventually, the front end must stall. At that point, your wide superscalar machine becomes idle. Superscalar performance is inseparable from cache performance. Data locality matters enormously. Now let's distinguish superscalar from SIMD. Superscalar means multiple different instructions executing simultaneously. SIMD means the same instruction operating on multiple data elements. Superscalar exploits instruction-level parallelism. SIMD exploits data-level parallelism. Modern processors combine both. You can issue multiple SIMD instructions per cycle. That's how modern CPUs achieve extremely high arithmetic throughput. Now let's talk about real-world IPC. If you have a 4-wide machine, you might assume IPC equals 4. In reality, average IPC for general workloads often falls between 1.5 and 3. Tight numerical loops can reach higher values. Branch-heavy code can collapse toward 1. This is why micro-benchmarks can be misleading. They are often written to maximize ILP. Real software contains unpredictable branches, cache misses, and complex control flow. Now let's consider power and thermals. Each additional issue slot requires more decode bandwidth, more scheduling logic, more physical registers, more bypass paths between execution units. Bypass networks, the wiring that forwards results from one unit to another, grow rapidly as width increases. More width means more wires, more capacitance, more energy per cycle. At some point, the performance gained per watt is not worth the cost. That's when industry shifted focus toward multi-core scaling. Instead of making one core extremely wide, we duplicate moderately wide cores. Now let's bring this back to software engineering. You may not design CPUs, but you design code that runs on them. Long dependency chains limit ILP. Unpredictable branches reduce effective width. Poor memory locality causes stalls that no amount of superscalar hardware can hide. Techniques like loop unrolling, reducing pointer chasing, minimizing unpredictable control flow, and improving data layout all help the processor find independent work. Superscalar CPUs are trying to execute multiple instructions per cycle. Your job, if you care about performance, is not to prevent that. Finally, let's look at the historical context. Early processors were scalar. Then pipelining increased throughput. Superscalar architecture allowed multiple instructions per cycle. Out-of-order execution allowed dynamic scheduling. Then multi-core extended performance beyond the limits of ILP. Superscalar design was one of the biggest leaps in single-core performance in computing history. It fundamentally changed how processors are built. Every modern high-performance CPU, whether Intel, AMD, Apple, or ARM, is superscalar. Different widths, different implementations. Same fundamental idea. If independent work exists, do it simultaneously. That's superscalar architecture. It's not marketing. It's not abstract theory. It's the reason your code runs faster when it's well-structured. And it's one of the core ideas you must understand if you want to truly grasp software execution at the hardware level. In the next deep dive, we'll dissect out-of-order execution and the reorder buffer in detail, because superscalar width without dynamic scheduling is only half the story. And once you understand both, modern CPUs stop being black boxes. They become predictable machines. I'll see you in the next one.